Okay, now we will start the training. Okay, and as you can see on the screen, what we're going to talk about today is about the RCNP, and the videos for RCNP is already online on the e-learning platform. And I want to ask that if you have watched the videos on e-learning, the about the RCNP routing and the switching technologies. Yes or no?
Yeah.
Okay, and actually, about this training, we hope that you have watched all the videos of RCNP before joining us, because we will not introduce each technology in detail, but it's just as you can see here, it's just a summary of all the content. Okay. So during this training, if you find that some topics we mentioned you are not that familiar with, so you can go to e-learning and watch the videos, okay, to get some detailed introductions. Okay, and if you have finished the RCNP R&S course by yourself, we hope that you can use the devices such as routers, switches, and for example, firewalls. Use this kind of devices to build a large campus network, and even establish the interconnection between headquarters and branches in some enterprise networks. Because all the contents about RCNP is used to build this kind of campus network or enterprise network. Okay, it can satisfy the requirement of most of the campus networks, or medium and even large size of campus networks. And in this course, we will summarize the technical content of RCNP R&S and complete the configuration of a typical network. So later you can see that in this course, we are going to give you a scenario, and in this scenario, it contains the typical. Sorry, sir, I need to mute your mic. And let's go on. As I said that, in this course, we're going to use a typical campus network as an example to show you the design of the network architecture, the application of the protocols, and the configuration of them. Okay. Firstly, let's see the background of this scenario. There is a company. Company A is a large listed company with many branches all over the country. And in order to improve the quality and efficiency of the collaborative office between the branches and headquarters, we decide to use the dedicated line to establish the connection. And the topology of this company's network is shown here. Okay, and let's take a look at this topology. The whole network is tiered into 3 parts. You can see on the left is the headquarters. Okay, we use a square to distinguish them. Okay, at the left is the headquarters network, and on the right is a branches network. Okay, between the headquarters and the branch, of course, is the ISP, is Internet Service Providers Network. Okay, and firstly, let's see the IP address design, okay, or IP address planning in this scenario. The interconnection network segment between devices is shown here. For example, between R1 and R2. Let's make it larger. Okay. Between R1 and R2, the subnet is 12.0.0.x. X means that at this side, at the R1 side, the IP address of the interface is 12.0.0.1, and that on R2 would be 12.0.0.2. So for the subnet between R1 and R3 is the same. It would be R13.0.0.1, 13.0.0.3. And here, R2, R4 is the same, 24.0.0.2, 24.0.0.4. Okay, so in this way, since we have a lot of IP addresses, a lot of interfaces, so it's very difficult for us to remember all of them. But in this way, during the configuration, it would be convenient for us to distinguish the IP address of each interface. Okay, and when you check the routing table, it would be more convenient to ignore the, for example, the destination address destined to. Okay, and in this, except the IP address planning, next is the technologies that will be involved in this topology. I listed here, and as you can see, we have covered most of the technologies in RCNP R&S. Okay, or in other words, most of the important technologies of RCNP R&S is involved in this topology. So we hope that after completing of configuration of this topology, you will be able to master the application scenario, the configuration, and some key points of the technologies in RCNP R&S. Okay, and okay, and as you can see, in the headquarters, the protocols we use first is VLAN. VLAN is very commonly used in the network, right? Because we use VLAN to trainer. Okay. Sorry. Okay, let's go on. First, about VLAN, we use VLAN to distinguish or to isolate the users. For example, in the enterprise network, we use VLAN to isolate the users in different departments. For example, R&D department in VLAN 10, financial department in VLAN 20, and marketing department in VLAN 30. So in this case, these users are isolated at layer 2, and we can make the broadcast domain much smaller, right? And smaller broadcast domain represents fewer broadcast packets, right? And in this way, we can reduce the usage of the bandwidth that occupied by the broadcast packets, and can improve the efficiency of the links. Okay, first is VLAN. Next is the DHCP. DHCP stands for Dynamic Host Configuration Protocol. It's a protocol that mainly used to assign the IP address to the network clients or network terminals. For example, the PCs, PC1, here PC1, PC2, PC3. These kind of PCs can get the IP address automatically through the DHCP. Okay, so, and in this case, here is a server different from the PCs. For example, for the laptops we use in the office, it will not affect the service if we get a different IP address every day, right? For example, today my IP address is 10.1.1.1, and tomorrow my IP address is 10.1.1.2. Since the forwarding entries will be learned automatically or dynamically, so it will not affect my network accessing. But for the server, it's different. Normally, the server offers service to the users in the network. So we prefer the server to have static IP. It has a static IP. So if we hope the server can get a static IP, we have two solutions. Firstly, we can manually configure it. Right? We can configure static IP address on this server, or we can do that through DHCP. For example, bind the MAC address of this server to a specific IP address. So each time when the server requesting for an IP address, the DHCP server will assign the same IP to the server. Okay, it's about the DHCP. And next is MSTP and VRP. These two protocols are often commonly used together. About the MSTP, firstly, you should know that MSTP is working mode of spanning tree. Right? Spanning tree is mainly used to calculate the topology and find out some ports, then block them. So in this way, we can solve the problems caused by layer 2 loops, right? By layer 2 loops. While MSTP is a multi-instance spanning tree protocol. Based on the STP, it can distinguish different VLANs into different instances. And then based on each instance, the MSTP can calculate or can convert the network into different topologies. So in this way, there will not be any links are totally free in the network. For example, VLAN 10 will go through GW1, VLAN 20 traffic will go through GW2. Or GW1 is a root in instance 10, GW2 is a root of instance 20. And in this way, since all the traffic of VLAN 10 goes through GW1, all the traffic of VLAN 20 goes through GW2. So we have to use VRP to work with MSTP. VRP is the Virtual Route Redundancy Protocol. Okay, it stands for Virtual Router Redundancy Protocol. And by using VRP, we can build multiple VRP groups. And in each VRP group, for example, let's clear this. For example, GW1 is the master. Okay, it's a master of VRP group 1, and so we say it's master 1, and GW2 is master 2. And in master 1, maybe its gateway address is the gateway, or it's a gateway of VLAN 10. So the traffic of VLAN 10 can go through GW1, and for GW2 is the same. It's a gateway of VLAN 20, so VLAN 20 traffic will go through GW2. This is the reason why we say that MSTP and VRP are commonly used together to do the to make the network more efficiency and can improve the. Hello everyone. If you don't have anything to discuss with us, please mute your mic. Okay. Okay, and let's go on. As we said that MSTP and VRP are the protocols to make the network have some redundant devices, redundant links, right? And redundancy in the network represents high reliability, right? Okay. Next is the AP. AP here is not the access point. It's not the wireless device. AP here represents or it stands for aggregate port. And here between the GW1 and GW2, we have two physical links. Let's make it clear. You can see between GW1 and GW2, we have two links. And these two links are building an AGG1. AGG1 means it's an aggregate port. The ID is 1. So in this way, logically, between GW1 and GW2, there is only one link. It's a logical link, okay, one logical link. And we can improve the bandwidth. This is about the benefits of aggregate port. First is about the bandwidth. We can increase the bandwidth between GW1 and GW2, and except that if one of the links is 40, we still have another link, right? So these two links are the backup of each other. We can improve the reliability of the network, right? It's a kind of redundancy, okay? And next is OSPF, okay? Later when we introduce the requirements in this topology in detail, you will know that actually between the HQ and the branch, okay, the HQ and the branch are running OSPF, okay? They are in the same OSPF area. Even across the ISP, they are in the same OSPF area. So they can calculate the routes in the enterprise network, no matter the HQ or the branch, okay? And it can find the optimal path to the destination inside the enterprise network, okay? And next is about the security. In the HQ, we have some security requirements. For example, we should enable the ARP spoofing. We should enable the DHCP snooping. For example, we should enable the global secure address binding. And these kind of requirements will be introduced in detail one by one in the following contents. Okay, and next is about the technologies in ISP. Okay, first is the OSPF. Here you can see R1, R2, R3, they are running OSPF, and the process ID is 100. Let me change the color. Okay. They're running OSPF 100, and they're in the area 1. The area type is a totally stub area. And at the same time, this port, you can see, this port G01 on R2 and G01 on R3 include the R4, R5 interfaces are in area 0, and between them, besides them, here is area 2, OSPF 100 area 2, and it's another spatial area which is totally NASA or totally NSSA area. Okay. And this is about the design of the OSPF. Then is the ISIS. Okay, ISIS is running on R6, R7, R8. You can see here, they're running ISIS. So in the ISP's network, we are running two different routing protocols. Okay, two different routing protocols. And since there are two different routing protocols, it would cause a problem. The problem is that OSPF and ISIS, they will not share their routing information automatically. But to establish the connection between HQ and branch, or to allow the accessing from the branch to the HQ, we hope that, or the purpose of us is to make the each corner in the network that are reachable. So on R6 and R7, firstly, R6 and R7 is has a special rule in OSPF. Do you know what it? Or what are they? What are R6 and R7 in OSPF? There is a special rule. Do you know it? If you know it, you can maybe share with us in the chat box. Yes, very good. ASPR, right? R6 and R7 are both ASPR. About what is ASPR is already introduced in RCNA, but let's see it together here. Since R6 and R7 is running both OSPF and ISIS. So it's connecting with another protocol, ISIS. And another protocol means it's another AS, another AS, okay? A numbers system. And in this case, we think that R6 and the R7 are at the border of the AS, at the border of the AS. So we call them ASBR. Okay. Oh, sorry. So we call R6 and R7 the ASBR. And for the ASBR, since it's running both OSPF and ISIS, so it can learn the root of OSPF, and at the same time, it can learn the IP address of, the root of ISIS. But as a router, it will not mix them. Mix them means that the ISIS root will not be forwarded to the OSPF neighbor, and OSPF root will not be transmitted to the ISIS neighbor, right? So to solve this problem, what we should do is the root redistribution. Root redistribution means that we should import the OSPF root into ISIS, import the ISIS root into OSPF. It's, in other words, we mix them, right? We mix them. And for example, if we import the ISIS root into OSPF on R6, so when you check the OSPF routing table on R6, pay attention here, it's the OSPF routing table. If you check the OSPF routing table on R6, you can find the ISIS root. It becomes a new OSPF root, but it's generated by ISIS. And in this case, R6 will share or will forward this root with its OSPF neighbors. We'll send it to R4, R7, and on R7 we should import ISIS into OSPF. So it will also be shared with the neighbors. And in this case, all the OSPF neighbors can learn these ISIS roots. And for the ISIS, it's the same. All the ISIS neighbors can learn the OSPF roots. In this way, all the routers in the ISP all the routers from R1 to R8, they can learn the IP roots. Okay, they can learn the root in the network. Okay, this is about the root redistribution. And another protocol we use here is the BFD. Okay. Firstly, we should know that BFD is not necessary. Okay, it's not necessary. Even without BFD, the whole network can still run properly. Okay, but why we need it, why we use BFD is that if we do not use BFD, OSPF, for example, OSPF, it can maintain the neighbor relationship by using the packet or the message. Here I want to ask, what's the message we use to maintain the OSPF neighbor relationship? Think about this. Hello, yes, hello. We use the hello package to maintain the neighbor relationship. How do we do that? Or how does the hello package maintain the neighbor relationship? For example, between R4 and R6, okay, R4 and R6, they will exchange, or they will send the hello package periodically. And in this case, it means that R4 will periodically send the hello packet. This is the hello packet to R6. And in this case, R6 can automatically receive the hello packet. And on the other side, it's the same. R6 will send it to R4. R4 can periodically receive it. But for some reason, R6 has not received the hello packet from R4 for a long time, R6 will think that, okay, R4 is 40, and the neighbor relationship between us will be affected. And when you check, you can see R6 has terminated the neighbor relationship with R4. This is how does a hello package to maintain the neighbor relationship. But if the R4 is 40, for example, if the device is 40, how long will R6 figure out the R4 is 40? You can think about this. How long? The time is based on the network type between them. For OSPF, it supports 4 network types. It supports broadcast, right? Broadcast, P2P, P2MP, and NBMA for network types. And normally what we use is broadcast or P2P. But no matter broadcast or P2P network, the time we take to figure out the failure of the neighbor is very long. It's 40 or 20 seconds based on the network type. But by using BFD is a protocol that can detect the status of the opposite or of the neighbor in a very, very short time, in milliseconds, okay? In milliseconds. So by using BFD can notice the OSPF that the neighbor is down, and then OSPF will disconnect or undo or disable the neighbor relationship immediately. Will not wait for the hello time. Okay, will not wait for the hello packet to time out. It can reduce the time we take to reconverge the network to milliseconds. Okay, it's a BFD. And next is BGP. Let's see the BGP design here. R1 is being BGP 100, and R2, 3, 4, 5, 6, 7 are in BGP 200, and R8 is in BGP 300. So since we have multiple BGP, how can I call it? We have different BGP numbers. It represents that we have multiple AS, right? We have multiple AS. And if we want to establish BGP neighbors here, we must have IBGP and eBGP peer, right? For example, between R1 and R2 is eBGP. It's an eBGP because they are in different AS. But between R2 and R4 is the IBGP peer. Okay, and later we will see the detailed information of BGP when we see the requirements. Next is the GRE over IPsec. GRE over IPsec in this topology is established between, you can see, between GW3, GW1, and GW3, GW2. So in this case, once they establish the GRE over IPsec, so through the VPN between them, we can think that our HQ and the branch are in the same network. Even we are crossing an ISP, but by using the VPN, we can think they are in the same AS, in the same network. And based on the GRE or IPsec VPN, we can establish the OSPF we just mentioned here. We can establish the OSPF neighbors, and we use a specific OSPF process ID, because here is 100, so we cannot use 100 anymore. We can use OSPF 200, OSPF 300. It depends. Okay, and in the branch, the requirement is quite easy. What we use is the super VLAN. We use the super VLAN to distinguish the, you can see the PCs in different VLANs, but use the same network segment. Okay. Then, after the overview of the whole topology, next let's see the requirements. Okay, First is the technical requirements in ISP. We're gonna introduce them one by one. First is the requirement of routing protocols. Here we use OSPF and RAID. Okay, in the topology is OSPF and ISS. It doesn't matter because no matter you use OSPF or ISS or RAID, the purpose is to learn or to get the roots of each other, right? Okay, and about this requirement, let's see. Here, you can see we have established OSPF neighbors, and here this quarter is area 1. The area type is totally stop area, and this is area 0. Area 0 is a spatial area, actually. Do you know what's the area 0 in OSPF? Or why we think that, or why we see that area 0 is spatial? Yeah, area 0 is a backbone area. Okay, backbone area means the routers in the area 0 or the how can I say, the LSDB. Okay, the LSDB of area 0 will contain all the LSAs in the network. Okay, no matter type 1, 2, 3, 4, 5, or even this kind of LSAs can be found in the area 0's LSDB. And here, the area 2. Area 2 is a totally NSSA area. Do you know what is NSSA? Or the difference between NSSA and stop? You can think about this. What's the difference between stop area and NSSA area? To know the difference, we just need to know redistribute route. Yeah, yes, it could be a difference. Because on the R6 and R7, they are in the NSSA area, and we redistribute the route from ISS into OSPF. Okay. Yeah. Yes. LSA 7 in the NSSA area, we could have type 7 LSA, right, or LSA 7, but in the totally stop area, no LSA 7, right? But why? Why we have LSA 7 in NSSA area? Actually, the main difference is that NSSA stands for no for AS. Actually, I don't get your point. What's the meaning for AS? Okay, here NSSA is not so stubby. Area. Okay, NSSA is not so stubby area. So it's a kind of stubby area, but not so stubby. The reason why it's not so stubby is that it's besides the backbone area. So, and it could be a stub, but at the same time, it's connected with another AS, right? It's connected with another AS. So for this kind of area, we don't hope, or we don't want these areas have the detailed information of the OSPF network, but we hope that some other AS can access OSPF from them, from the NSSA area. So this kind of area could be NSSA. Okay. So this is about the stop and NSSA. But what's the when we talk about the LRC types, here I want to ask, firstly, in the stop area, we can see which kind of LRCs or which type of LRCs. For the stop area, we can see what type of LRCs. We have type 1, type 2, type 3, 4, 5, and 7. Actually, we have 6, but 6 is not used in unicast. So 1, 2, 3, 4, 5, and 7. What can be found in stop area? Okay, I see an answer is 1, 2, and 3. 1, 2, and 3. Okay, so how about totally stop? How about totally stop? What type of LRCs can we find?
Luigi.
Okay, I saw an answer here include all the spatial areas, right? So we can see the answers together. Okay, stop area reject type 4, type 5. So we have 1, 2, and 3. Totally stop reject 3, 4, 5. Here I want to ask, if totally stop area reject type 3, 4, and 5, it means that there could only be 1 and 2. You think is correct or incorrect? Totally stop only have type 1 and type 2 LRC. Yes. Except type 1 and type 2, there is a type 3 default root, right? Well, sorry for that. Okay, for the totally stop, it has 1, 2, and 3. But here, the type 3, normally the type 3 LRC is used to transmit or is used to carry the roots which destined to the other network, right? But here, the type 3 is just a default root, okay? It's just a default root. It's not a detailed root. Default root means that the ABR send a type 3 default root to all the other routers inside the stop areas. It means that if you want to go to the other areas, just send the package to me, okay? Okay, and next is about this is totally stop. Next about the NSSA. Which type of LRCs can be found in NSSA? Here in the answer just shared in the chat box, it says reject 4 and 5, but allow local redistributed routes. Or if we ask the LRC type, it would be 7, right? 7. So different from except 1, 2, 3, there is another type, is type 7. Type 7 here, you should know that the type 7 LRC in the NSSA area is similar, or in another word, the function of type 7 LRC in the NSSA area is the same as that, is the same as the type 5 LRC. Okay, the type 5 LRC is used to carry or is used to transmit the external routes. Okay, the external routes. And the totally stop, totally NSSA. What's LRC types in totally LRC? different from NSSA area. Total NSSA do not have the type 3, but have a type 3 default, right? Type 3 default. Okay, so this is about the spatial areas and the LCA types. You just need to remember this. You will know the working principle of the spatial areas. And here, let's see the scenario why we should set this kind of areas to be totally stub or why is totally NSSA. If we just use the common area, it works actually, right? Even we do not use a spatial area, it will not affect the service. But why we use the spatial areas here? Anyone knows the reason? Reduce flooding, right? Okay. No matter in which case, we use the spatial areas to reduce what? Reduce the LCAs, reduce the root entries, the number of root entries, right? If we do not, for example, if we do not set the area 1 to be the totally stub, R1 can learn the detailed root of all the network, right, of all the network. But if we set it to be the totally stub area, you will, when you check the IP routing table on R1, you can see that there is only one default root, and here maybe two because it have two OSPF neighbors. So there will be two default routes guide the traffic inside the guide the traffic on R1 to the maybe to other areas, even to the external network. So we can reduce the number of routing entries in the IP routing table, and we can reduce the number of LSAs in the LSDB. It's mainly suitable for the device lower end devices. Right? For example, those kind of routers cannot operate such a large number of routing entries or such a large number of LSAs. So we use the spatial area. Okay, so about this part, I think it's easy for you to understand it now, right? The working principle of spatial areas and the reason why we use them, why we use spatial areas. Okay, and next is about the BFD. Okay, BFD. Normally, after using BFD, you can see R1 and R2. Between R1 and R2, they are establishing the OSPF neighbor. Okay, and then at the same time, we have enabled BFD. So the OSPF neighbors has established, and at the same time, they have established the BFD neighbors. Okay, and now once the network is 40, let's see. The link between R1 and RSW1 is disrupted, you can see. Some fault occurs in the network. And once the fault occurs, who will know or who will sense the fault first? You can see. Firstly, BFD will sense the failure in the network and then set the session state to done. So at this time, firstly, BFD will set the BFD session state. Pay attention here. BFD session state to done. And then BFD notifies the local OSPF process that the BFD neighbor is no longer reachable. Since the BFD neighbor is the same as the OSPF neighbor, so once the BFD session is done, then the OSPF process will tear down the OSPF neighbor relationship. And if a backup path is available, data forwarding will be switched over to the backup path. And in this case, we can reduce the time of network recovery, right? Because no matter what's the failure, no matter if you have a backup path or not, without BFD, the OSPF neighbor maintenance is based on the hello package, and it will take at least 20 seconds. Of course, the default time, the default the minimal default time is 20 seconds in the P2P, right? In the P2P network, and in the broadcast network, the default time is 40 seconds. So in this case, by using BFD, we do not need to wait for the confirmation of hello package, and we can tear down the OSPF neighborhood ships in a very short time. And we can, in this case, we can switch to the backup path in a very short time. And in other words, it can reduce the effect of the service when a fault occurs in the network. Okay, this is about the application of BFD and OSPF. Okay. Next is about the route redistribution. Firstly, about the route redistribution, we should know what is it. Okay, we should know what is it. Here we can see an example. We have three routers: R1, R2, and R3. On R2, you can think it's running RIP and OSPF at the same time. So when you check the routing table, you can see the routing table on R1. You can see the RIP. You can see RIP routes. R represents RIP. Okay, you can see the RIP routes, and you can see the OSPF routes. O represents OSPF. But by default, on R1, it can only learn the, you can see it can only learn the 192.168.1.0 and 2.0, the local routes, but cannot learn the routes here, the routes in OSPF. And for the R3, it's the same. By default, it can only learn the local routes, but cannot learn the routes here in RIP network. But after route redistribution, you can see we configure the route redistribution on R2. Use the configuration router RIP, redistribute routes OSPF1, router OSPF1, redistribute RIP sublets. This is a command. Okay, this is a configuration command. And after this, you will find that the RIP routes, you can see the RIP routes on R2 has been redistributed to R3. Okay, to R3. And the OSPF routes on R2 has been redistributed to RIP and will be shared with R1. Okay, so you can see on R1, we can even see the routes to 3.0 and 4.0, but which difference is that it's not an OSPF route anymore. It becomes a RIP route because we redistribute or we import the OSPF route into RIP. So it becomes a RIP route. And we, on the other side, it's the same. If we import, you can see import the RIP route into OSPF, so it becomes a OSPF route and you can share with the OSPF neighbors. Okay. So in this case, we can share the routing information between different route protocols, but at the same time, you should know that actually even R3 has learned the route to 1 and 2, 1.0 and 2.0. But actually, you can see no matter the OSPF or no matter the protocol or some other route attributes has changed. For example, you can see the preference of the route has changed. The network type of the route has changed. Okay, so when we do the route redistribution, we should pay attention to the attributes of the route after redistribution, because sometimes it would cause some problems after route redistribution. And the problem we mentioned is shown here. Let's see it. Now, you can easily find out R6, R7, R8 is just this is a part, right? This is a part of the topology we just seen, of the whole topology. And on R6 and R7, we do the route redistribution. Means that we import, you can see, we import RIP route into OSPF and OSPF route into RIP. on R7 is the same. RIP route into OSPF, OSPF route into RIP. Okay. And in this case, you can see when we check the protocol routing table on R6, you can see that firstly we should know what is the protocol routing table. Actually, on a router or on a layer 3 device, it has multiple routing tables. When we use a command show IP routing table, what we check is the global routing table. Okay, we can call it global routing table. Global routing table means that it's inside the global routing table is the optimal route to the destinations on the entire router. But it doesn't mean that it's all the routes on the router. Okay, all the routes on the router. For example, now on R6, in the RIP, you can see in the RIP routing table, it has a route to 8.8.8.8/32. And the next hop is 68.0.0.8. The next hop is which? Is R8. It means that from R6 to 8.8.8.8, we can go through this way, right? From R6 to R8 and through the low back interface on R8. But there is another route, 8.8.8.8/32, to the same destination, but the next hop is different, which is 67.0.0.7, which is R7. Where does this route comes from? Think about this. Because R7 and R8 are running RIP. So R7 can learn the route to 8.8.8.8 through RIP. And in the RIP routing protocol table, you can see the route to 8.8.8. And if we import it into OSPF, so in the OSPF routing protocol, there would be a route to the loopback interface on R8, and it will be sent to R6 through OSPF. So actually, in this case, at this time, on R6, we have two routes to the same destination. And here I want to ask, which of it will be added to the global routing table? Think about this. Which? The RIP route or the OSPF route? Oh, why? Because we said that the RIP route guide the traffic from R6 directly to R8, but the OSPF route guide the traffic from R6 to R7 and then check the routing table on R7. Obviously, RIP route is better. From our point of view, from our eyesight, the RIP route is better. It can directly guide the traffic to R8. But why we think OSPF will be added to the global route? Okay, I saw the answer, right? I saw the answer. Lower AD, right? Lower AD. Because RIP, yeah, because of AD, right? Or in another word, the priority or the preference of OSPF routes of OSPF is higher. So when we compete, which is, or when we determine which route is better, firstly we will check the destination. To the same destination, firstly the route with the lower AD, with the lower AD will be the optimal route. So here OSPF is better, and on R7 actually is the same. This OSPF route is better, but here comes a problem. Let's see if it's like this. The packet, for example, we have a packet here. This is a packet. The destination of this packet is 8.8.8.8. So it will have a problem. Do you know what's your problem? You can analyze it by yourself. What's your problem? What's the problem that would occur in this case? You can see the packet will be forwarded by R6, and R6 will check the IP routing table, and we see, as we said, this route will be added to the IP routing table. So the next stop is R7. So this packet will be sent to R7, and R7, after receiving it, R7 will check the IP routing table for the destination and will match this route. The next stop is R6, so it will be forwarded to R6. R6 will send it to R7, R7 will send it to R6, right? So here comes the problem. Even the packet cannot reach the destination. Okay, this is also called the layer 3 loop. Okay, layer 3 loop. But in this case, you can find that the improper route redistribution will cause two problems. The first problem is the layer 3 loop, and the second possible problem is the suboptimal routes or suboptimal paths. Okay, and to solve this problem, what can we do? Think about this. How can we solve this problem? Actually, we have a lot of solutions. Okay, we have a lot of solutions, and here we just introduce one method. Okay, for all the routes here, all the routes redistributed from RIP to OSPF, we will give them a tag. For example, the tag is 100. And then, since they have a tag, and when on R7, we should filter all the routes with tag 100. And here, it's the same. Here, we have a tag 200. And on R6, we filter all the routes with tag 200. In this case, R6 will not learn the routes or the external routes. The external routes, for example, 8.8.8.8. R6 will not learn this route from R7 anymore, and it means that this route will not exist. And on R7 is the same. This route will not exist, and all the traffic to 8.8.8 will be forwarded through RIP, will be directly forwarded to R8, and we can solve this problem. And how can we tag these routes? How can we tag these routes? We should use some tools. Right? For example, we can use the route map. Okay, we should use a route map to do that. Later, when we introduce that configuration, you will see how to use route map to tag the routes and to filter the routes. Okay, this is about the route redistribution. And next comes to BGP. Before we introduce BGP here, I want to say that we have configured the IP address of all the interface. Then we have configured the OSPF. We have configured the RIP, right? OSPF and RIP. And then next is the route redistribution. So until now, all the routers in this figure, you can see all the routers in this figure are reachable to each other. Are you agree with this? Are you agree with this? Yes or no? Please give me some feedback. Yes. Okay. Yes. This is what we do. Okay. From here you can know the OSPF, the ISS route redistribution, what we configure. The purpose of all what we have done. The purpose of all what we have done is to ensure the reachability in this figure. This is just the purpose. But why we should do that? Or why we should make ensure the reachability in this figure because we want to establish the BGP neighbor. Okay, BGP. It's step by step. Next step is BGP, and let's see what we do here. Firstly, in this figure, you can see I have point out the BGP peers. Here is BGP 100. You can see BGP. Let me change another color. Okay, this is BGP 100, BGP 200, BGP 300. So the BGP peers inside the CMAS are IBGP, 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 IBGP. Okay, we use the orange color to represent the IBGP, and the between R1, R2, R1, R3, or R6, R8, R7, R8, they are eBGP neighbors. Okay, they are eBGP neighbors. And after establishing the BGP neighbor, why we should use BGP? Think about this. Why we should use BGP? About the protocol BGP, firstly, different from OSPF or ISIS. Here, let's say it. For all the routing protocols, could be tiered into two types. The first is called IGP, and the other is ease of traffic engineering. Yeah, maybe. Okay, we will see it later. Okay, we will see the reason why we use BGP later. And here, let's see it. All the routing protocols can be tiered into IGP and EGP. IGP is the Inter-Rail Gateway Protocol. It stands for Inter-Rail Gateway Protocol. For example, OSPF. For example, ISIS. For example, OSPF, ISIS, and RIP, and maybe EIGRP. Sorry. Okay, EIGRP. These protocols are IGP. And do you know the main function of IGP? For example, OSPF, ISIS. These kind of protocols are used to calculate the network, to calculate the routes. I agree with that. The IGP are used to calculate the routes, or are used to replace the static routes. They can dynamically calculate the routes and allow or ensure the communication inside the AS, right? Or no matter OSPF or ISIS or RIP or EIGRP. And the EGP is the exterior, okay, the exterior gateway protocol. They are used inside AS. Okay, IGP used inside AS, and the EGP is the exterior gateway protocol, and the protocol we are using nowadays is BGP, right? BGP is the EGP we're still using nowadays. Okay, and BGP is developed based on EGP. So EGP is a name or is a type of it's a name of the type of routing protocols, and at the same time, it used to be a protocol. Okay, and the BGP is used. You can see here, BGP is used between. Or can be used. Okay, can be used between AS. You can see AS100, AS200, we use BGP. And in other words, IGP is used to calculate routes, but BGP is used to carry or transmit routes. The BGP protocol itself will not calculate any routes. It just transmits the route from one side to the other. So here, obviously, what we use BGP is to transmit the routes from the left, from the HQ to the branch. Okay, so here is the reason why we use BGP, and it would cause a problem. Let's see it. I think you're clear with this part, right? About IGP and EGP, so I will just clear it. And then let's see here. Let's see. Here we use BGP to establish the BGP peer. So R1 and R2, 3, 4, 5, 6, 7, 8, they are using BGP. So the root, for example, the root, here is a root, maybe 11.11.11.11/32. This root, if I want to, for example, carry or transmit this root to R8, based on the, you can see, based on the information in this figure, will it succeed or not? You can think about this. Based on the information or based on the BGP peer in this figure, can we transmit the root 11.11.11.11/32 from R1 to R8? You know it? Actually, it could be a little difficult. Okay, it's a little difficult. We will feel, okay? We will feel because, or the result will be that R8 cannot learn this route. R8 cannot learn this route, and the reason is that it's about the BGP route forwarding policy. Okay, route forwarding policy. The E peer, you can see here, for R2, now R2 is receiving the route 11 from the eBGP peer, right, from the eBGP peer. So based on the BGP route forwarding policy, the route from the eBGP peer will be forwarded. The route from the eBGP peer, right? This is a route from the eBGP peer R1. It will be forwarded to eBGP and IBGP neighbors. So R4 and R3 can learn. So on R4, it can learn the route 11.11.11/32. And on R3, it's the same. But for R6 and R5, they cannot learn the route 11. The reason is that the route, based on the BGP route forwarding policy, the route from the IBGP neighbor will not be forwarded to the IBGP neighbor anymore. Okay, this is a policy, and we can take a moment to think about this. Why the route from the IBGP neighbor cannot be forwarded to another one, to another IBGP? it's very easy because the root 11 is forwarded to R4, R4 forwarded to R5, R5 forwarded to R3, R3 forwarded to R2. Here's a loop. Yeah, split horizon. Yeah, very good. It's a split horizon to avoid loop. Okay, split horizon. And so in this case, let's get back to the question I just asked. Since R1 cannot forward the root or 11 to R8, so in this topology, let's get back to, let's see. In this topology, R1, this is a simplified topology. R1 cannot forward the root to R8. So in this case, it means that GW1 cannot communicate with GW3. GW2 cannot communicate with GW3. But what we want is to establish the GRE over IPsec between them. To establish a GRE and IPsec VPN, the basement is that GW1 and GW3, GW2 and GW3 can communicate with each other. But in this scenario, the roots cannot be forwarded from left to right. So how can we solve this problem? Okay, this is about the how to break the split horizon, or how to solve the problem caused by split horizon. We have two solutions. Okay, we have two solutions. The first solution is what? Think about this. Root reflect, yes, it's a very good solution. We call it RR. Okay, we can use root reflector to solve this problem. Root reflector is actually the solution we use in this in the lab, in the summary lab. We can set R4 and R5 to be the root reflector. This is RR and RR. This is RR and RR. Okay, and except that R2, R3, R6, and R7, all of these four routers are the client. Client, we use C to replace it. Client. And the working principle of RR is that all the root from the client, you can see all the root from the client will be forwarded or will be reflected. If we use root reflector, we use reflect. Okay, reflect. All the root from the client will be reflected to all the neighbors, no matter it's a client or non-client. So in this case, 11.11.11.11 will be reflected by R4. So all the routers R6, R7, R5, and here is another RR, so it will reflect the roots. Right? So in this case, all the routers can receive, of course, include R8. This is the first solution. We call it root reflector. But actually, root reflector is not included in RCNP. Okay, it's not included in RCNP. So we still have another solution. Do you know it? Nico? 4-mesh. Yeah, very good. The other solution is 4-mesh. Okay. You must have a very deep understanding of BGP, right? 4-mesh. 4-mesh means that all the routers establish the, let's clear this. All the routers establish the IBGP peer between each other. Since here, R2 and R4 are the IBGP, so 4-mesh means R2 should establish the IBGP with R4, R6, R3, R5, R7 directly. Since in this case, R2 and R6 are the IBGP neighbor, so the root 11 will be directly forwarded to R6, right? And this is the EBGP, you can see the root from the EBGP neighbor forwarded to IBGP neighbor R6, R7, R5, R3, R4. So this is also a solution to solve this problem. Okay, and later when we introduce the lab, you can see what we use is root reflect. But if you find that the root reflect is difficult to understand in the RCNP stage, so you can use the for mesh. The configuration could be a little complex, right? But actually it's not difficult, right? It's very easy to understand. Just enable the IBGP peer with all the other routers in BGP 200, in AS 200. We can solve this problem. Okay, this is about the BGP, and next is the GRE over IPsec. Okay, since we're introducing GRE over IPsec, so I simplified the ISP part and the R1, R8. Okay, and since after using BGP, pay attention here, after using BGP, we can forward the route 10.0.0.0/30 and 20.0.0.0/30 and include the subnet here 30.0.0.0/30 to the neighbor. So in this case, by using BGP, we achieved that GW1, GW2, GW3, they can communicate with each other, right? This is why we use BGP. And since they have the connection or the communication between each other, so we can establish the GRE over IPsec. Okay. Once the GRE over IPsec has established GW1, GW2, and GW3, we can use OSPF. They can run OSPF. This is also a very important point. If we want to use the OSPF based on the VPN, what you can use is GRE over IPsec. Okay, GRE over IPsec. Okay, so this is about the GRE over IPsec, and until now, since we're running OSPF, for example, OSPF 300, in this case, the routes in HQ and the routes in branch can be calculated by OSPF, since they are in the same OSPF process and even in the same OSPF area. So it's a totally integral network, or a totally internal network. And it's very simple for the PCs to communicate with each other. PC1 communicate with PC4, PC2 communicate with PC4, PC5, and the client. Okay. This is about the ISP requirements and the solution to the requirements. About this part, do you have any questions? How do we achieve the goal state by state? First, the IP address planning, then OSPF, ISIS, then route redistribution, then BGP, right? And then GRE over IPsec, and then OSPF, then done, right? So actually the principles or the protocols we use here have their very important, each of them have their very important rules, right, to solve different problems. Okay, since you don't have, since I don't see any questions about this part, so let's go to next part about the technical requirements in HQ. First is about the IP address planning. It's easy to understand, right? VLAN 10, VLAN 20, and the subnet of VLAN 10 is 192.168.1.0/24. VLAN 20 is 2.0/24. And we have a route server, as we said that normally server should have a static IP address. So it's in VLAN 20 and the IP address is static 192.168.2.200/24. And we cannot manually configure it. We must use DHCP to assign the static IP address. Later we will see how to do that. And next, MSTP VRP. MSTP VRP runs between GW1, GW2, L1, L2. L1, L2 are the access switch. VLAN 10, VLAN 20 are used between two instance 10 and 20, respectively. Root of instance 10 is GW1, 20 is GW2, and the master of VRP group technical department is GW1, and the other master is on the other side on GW2. This is just the VRP and MSTP we just mentioned at the beginning, and later we will see the detailed design. Okay, and the next, the two interconnection links of GW1, GW2 perform layer 2 static. First is a layer 2, and then it's a static port aggregation. Because about the aggregate ports, we have static mode and the LACP mode. Right here, what we use is a static mode. Data load balance mode is based on the source and destination MAC. Okay, this is the load balance mode of the aggregate port. Okay, interface type is trunk. The information is here. Trunk, VLAN 10, 20, 800 allowed. So about the trunk, we should configure the allowed VLAN. And servers in VLAN 20 provide Telnet SSH service. Servers must be connected to the branches, but cannot be pinged. Pay attention here. Cannot be pinged means that we should have some methods to filter the ping packet. And the ping packet is based on RCNP. So we should use some tools, for example, ACL, to block all the RCNP packets from the client to the server. Okay, this is about the technical requirements about the server, and then OSPF 300 runs. So here we run OSPF 300, GW1, 2, and 3. Use VLAN 800 to establish the neighbor. So, but on VLAN 1, on GW1, GW2, GW3, we have VLAN 10, 20, 800 at the same time. How can we just use VLAN 800? Sorry. How can we only use VLAN 800 to establish the neighbor? It's about the feature of OSPF. We call it silent interface. Okay, silent interface. Later we will see. Next is about the security. About the security policies. Global secure address binding. Bind the PC1's IP address and MAC address globally. Configure the port on access switch where PC3 resides as a layer 3 security port, and detect the violation packet, discard it, send a trap. This is about the action we take when we detect the violation port. Prevent unauthorized IP address and DHCP server access. This is requirement is about DHCP snooping. Configure port loop prevention for L1, L2 access switches, and action is block port. This is about the ILDP. Enable ARP anti-spoofing for all interfaces and shut down all unused interface. This is about the layer 2 security requirements and how to satisfy all the requirements in HQ. Let's see. First is about the MSTP and the VRP. Now, the requirement is that GW1 is the root of MSTP instance 10 and is a master of VRP instance 10. GW2 is the root of instance 20 and master of VRP instance 20. Firstly, we should know how to achieve that. How to achieve that. To control the root and the master election, no matter in MSTP or VRP, is to modify some of the parameters, right? To modify some of the parameters. For example, the election of the roots is firstly we compare what? Here I want to ask. Now, no matter in STP or RSTP or MSTP, when we elect the root, or the election of the root is based on what parameter? Bridge priority, yeah. Firstly, we compare is the priority. But when we compare the priority, we prefer the larger priority value or the lower priority value. Do you know it? Lower, yeah, lower. So firstly, we compare the priority and we prefer the lower value. But sometimes, since the priority has a default value, right? The default STP priority value is 32768, right? 32768. Okay. So when both of the switches, for example, GW1, GW2, when both of them are using the default value, so we cannot determine based on the priority. Then we should compare the MAC address. So in this case, to control the roots of each instance, we can modify the priority of GW1 and GW2 in different instances. Right? We can ensure that GW1 has lower priority in instance 10, and GW2 has a lower priority in instance 20. For the master, it's the same. VRP master election is also based on is also comparing the priority first, and also prefer the lower priority. Okay, this is about the MSDB and VRP. After configuring the priority value, we can ensure that this GW1 is the root and master of instance 10. GW2 is the root and master of instance 20. And then let's see, how does the traffic forwarding? We use the red square. We use the red square to replace the traffic of VLAN 10, and the blue one represents the traffic of VLAN 20. So let's see it again. VLAN 10 packets are forwarded GW1, GW2, GW2. Okay, so I saw your answer. Thanks a lot. Okay, and you can see this is about the MSDB and the VRP working principle. How do we control the root and master? And after the configuration, how does the traffic forwarding? Okay, and next is about link aggregation. GW1, GW2, we establish aggregate ports. Okay, since it's a static aggregate port, so it's not that complex. Okay, and let's see the configuration. Interface range G01 to 02, port group 1. So we bind them. And into aggregate port 1, switch port mode trunk. Switch port trunk allow VLAN 10, 20, and 80. Okay. And if we only allow, pay attention here, on reject switches, we by default we allow all the created VLANs. Okay. For example, we create VLAN 1, 2, 3, 4, 5, 6, 7, 8. So once we create them, they are allowed to go through the trunk. So if here comes a problem, if we only allow 10, 20, 80. For example, there is another VLAN 100. So we should accept this command. We should disable, right? We should or block some other VLANs. But since in this case we don't have other VLANs, so it's not necessary. And this is important. Aggregate port load balance south-west IP. So the load balancing is based on source and destination IP address, or source destination MAC. Right? It's based on the requirements. Here, the requirement is source and destination IP, but in our lab, you can see in our lab is source and destination. Okay, where is it? Okay, here, source and destination MAC. So the command would be src dst MAC, right? So when you do a configuration, pay attention to the requirements. And the next is that since we have a requirement that we let's get back to the requirements. Okay, between GW1, 2, 3, we run VLAN 300, but use only 800 to establish the neighbor. It's about the silent interface, or it's called passive interface. Let's see how that works. When an interface on a router is configured as a passive interface, the interface no longer sends hello packets. What's the function of hello packets? Think about this. What's the function of hello? It has two functions. Yeah, first is to establish the neighbor, except that it can maintain or keep alive. Yes, keep alive the neighbors. So if once the interface is configured as passive interface, it will not send hello packets anymore. So in this case, if we configure with SVI10 and SVI20 to be the passive interface, so it will not send out hello packets anymore, and we can only establish the neighbor based on VLAN 800, so can satisfy the requirement. Yeah. Okay, so you can see the configuration passive interface G01, and think about the configuration on our devices: router OSPF 300, passive interface VLAN 10, passive interface VLAN 20. Okay, so it's a very easy requirement. Just use the passive interface. Next is about the security requirements. Let's see. Global security address binding. Now, let's see an example here. There are two global security address binding modes. After the MAC and the IP address binding is configured in global configuration mode, a command needs to be run for the security address to take effect. You can see the two different modes is showing here: IP address, IP version 4 address, and MAC binding, or IP version 6 address and MAC address binding. So it's supported no matter in IP version 4 and IP version 6. And the IP address and MAC address binding function applies to all ports of the device by default. So once you enable, since it's global, you can see global security address binding. So all the device will, all the interface or all the ports will get the binding information. And you can configure exclude ports on which this function does not take effect. Normally, the excluded port is the, you can see here, is the uplink port. Okay, it's the uplink port. And next, let's see, it's about the security address binding. This is a layer 3, okay, security address binding method and the violation actions. The modes could be static binding or dynamic binding. From the name, actually, we can easily figure out the difference. For the static binding, we manually run commands to bind the layer 2 or layer 3 security addresses. But dynamic means a switch automatically learns addresses and converts them to security addresses. A switch can only learn layer 2 security addresses, okay, not layer 3. So for this kind of switch, access switch, this is a normal user, PC1, and this is a hacker, right? So to prevent the attack from the hacker, we can bind, right? We can bind the IP address and the MAC address of the PC1. The maximum number of security addresses can be configured in both modes. The default maximum number is 128. Right? It's quite large. it's a quite large number. Limitation on the number of security address prevents MAC address entries from being exhausted by a MAC address scanning attack. And once, next is a violation action. Once the, for example, once we detect that there is any violations, what we can do to solve the problem. The first action is protect, and this is the default action. Violated packets will be discarded when a port security violation event occurs. So we just discard the packets. Next is restrict. A trap notification is sent when a port security violation event occurs. Or shut down. Shut down is obvious. Once the violation occurs, the port will be disabled. The port is disabled and the trap notification is sent when a port security violation event occurs. Okay, and this, since the port is disabled, so if you want to recover, you have to do it manually. Okay, this is about the security address binding, and next is about the IODP. Since we said that on the access layer, we should use some loop prevention protocols. So the IODP is used in this case. Let's see. IODP is mainly used on access layer switches, so different from STP. Even IODP is also a kind of loop detection protocol, but different from STP. It's mainly used to empty the loop or empty the local loop. In these two scenarios, for example, this is an access switch. We use you can see we use a cable to connect two local interfaces, or it's connected with a hub, but on the hub we have a cable connect to two local interfaces. Okay, so this is, in this case we can use IODP, and the working principle of IODP actually is quite easy. IODP will send out the packet. It will send out the packet periodically, and once it can receive, for example, once it can receive the packet from itself, so it's for L1 loop. No, not L1 loop, you mean physical loop, right? With layer 1, we cannot say that because layer 1 is a physical layer, but normally most of the even layer 2 loops are caused by for example, improper physical connections. So you can just think it's used for this kind of scenarios that the self loop, okay, switch self loop is also layer 2 loop, but different from STP. STP is used for example, the loops between multiple switches, but IODP is mainly used for this kind of self loops. Okay, for example, improper connection on two ports on the same switch. Okay, and once the IODP detects, for example, in this case, IODP detects there's a self loop, no matter on the switch or the hub, it will take some actions. First is block. Block means logically block the port. Okay, block the port. Or shut down the port, set the port in arrow disabled state. Shut down the SVI, disable the port SVI. Or warning. Warning will generate an alarm. Okay. It's a very easy protocol actually. Compared with RSTP, it's quite easy. Okay, and next is ARP spoofing. Let's see it. No verification mechanism. A device or PC does not verify the identify of ARP package when ARP learns mapping relationships, and later takes precedence. The device or PC always update the ARP caching table using the latest ARP packets. And based on these two mechanisms, it will cause some problems. Okay, And let's see, these are two vulnerabilities that are exploited by ARP spoofing. For example, let's see the description here. When communication with B, A broadcasts an ARP packet to request the MAC address of B. Okay, I think you since it's the basic of the network, I think you are familiar with the ARP working principle. ARP is mainly used to request the MAC address of one specific IP, right? So when communicate with A, B will send, sorry, when communicate with B, A will send the ARP packet. ARP request is a broadcast packet to request the MAC of B. And then after receiving that, since it's a broadcast, you can see, since it's a broadcast packet, so B and C can receive it. But normally, after receiving it, C will just ignore it because the MAC address is broadcast, but the IP address is the IP of PCB. So normally, PCC will just ignore it. But for some reason here, for example, PCC is an attacker. So C send a forged ARP response to A. In the response, sender IP, pay attention here, sender IP is that of PCB, is 1.2, while the MAC is PCC. So after receiving the reply from PCC, PCA will not figure. PCA cannot send that. It's a attack from an attacker. It will just record it into the local ARP table. And then C send a forged response to B, in which sender IP is 1.1. There will be another ARP reply to B, and the IP address is 1.1. MAC address is PCC. So in the PCC's MAC ARP table, the IP address 1.1 is binding with MAC address C. So in this case, it will, here comes a problem. Each time when PCA wants to send packet to PCB, it will send to C, and then C can check the packet. For PCB, it's the same. When PCB wants to send packet to A, it will send it to PCC based on the ARP table. So all communications between A and B go through C. Both A and B are deceived. Okay, so this is a problem caused by these two mechanisms. No verification and later takes precedence. Okay, and you can see here the packet. Okay, just like what we say, the traffic between A and B will be monitored by PCC, and even will be rejected by PCC. Okay, this is about the requirement of ARP spoofing. And then let's see, how does ARP spoofing and how does gateway spoofing works? C send a response to A in which the sender IP and the sender MAC are changed to 1.254 PCC respectively for the purpose of deception. However, actual sender IP is 1.3. So in this case, PCC acts as the gateway. In normal cases, access switch receives the response only from the opting port G024. Response from other ports indicates gateway ARP spoofing. And to protect the device from gateway ARP spoofing, what we should do is to firstly configure the correct gateway IP address on all the ports, but the opting ports. Verify the sender IP in ARP response from the ports other than the opting ports. If the sender IP is the same as the gateway, discard the packet because the gateway is connected with G024. But if I receive a packet which IP is 1.254 from G03, it's very obvious that this is a gateway ARP spoofing, and we just discard the packet. And in this case, we can protect. Okay, we can protect the network, and the configuration is quite easy. In the interfaces, other than the uplink ports, 1, 2, 3. You can say 1, 2, and 3. In this port, anti-ARP spoofing IP 192.168.1.54. So in this case, we can tell all these ports, all these 3 ports, that the gateway is 1.254. Okay. And if you receive which sender IP is this IP address, means this is a gateway ARP spoofing, and please discard the packets. Okay. You can see it's blocked. And at last, let's see the requirements of the branch. Actually, the requirements of the branch is quite easy, which we have only one subnet. You can see we have only one IP address segment, but there are 3 departments. We want to isolate them in there too. So what we can do is to use the super VLAN. And let's see how the super VLAN works. A super VLAN contains multiple sub VLANs used to isolate the broadcast domains in a physical network. The sub VLAN can use the same, you can see, same IP subnet and default gateway, but they are isolated at layer 2. Super VLAN is the VLAN which owns the subnet. For example, create layer 3 SVIs, configure the subnet gateway IP. Super VLAN contains no physical ports. Pay attention here, no physical ports. To manage the physical ports, we use sub VLAN. Sub VLAN contains only physical ports and are used to isolate layer 2 broadcast domains. ARP proxy function needs to be enabled for the super VLAN and sub VLANs for communication between hosts in a sub VLAN and external hosts, and even between sub VLANs, because they are isolated in different broadcast domains. So by default, they cannot use ARP to request the MAC address of each other. In this case, we have to enable the ARP proxy. Only in this case, they can get the MAC address of others. Okay. For example, we have 3 sub VLANs: sub VLAN 10, sub VLAN 20, sub VLAN 30. And each sub VLAN is a specific broadcast domain. But all of them can use the same subnet, 172.16.1.0. And they belong to the same super VLAN, which is 100. And we use the super VLAN to configure the SVI interface, and the SVI 100 will act as the gateway of all the clients in each sub VLAN. Okay, so this is about the overview of the super VLAN. And until now, actually, we have introduced the summary course, and we have reviewed most of the important points in RCNP R&S together. And the next part, it will be we're gonna see the lab together, because we think that it's very important for us to master the configuration of all these protocols. Okay, so just now we just introduced the requirements, and we analyzed the requirements. We have know how to satisfy the requirements of the whole topology. And next, what we should do is to use the commands to achieve that. Okay, and before we start this part, how about this? Let's take a rest for 5 minutes. As you can see, this is the lab guide. Okay, this is a lab guide for the configurations. And since we have already introduced the background and the requirements, so let's just see the configurations together. Okay, we will take some time to go through it. Okay, you can see on firstly on R1, 2, 3, 4, 5, 6, and 7, we should enable OSPF. It's just the basic configuration of OSPF. I think you are very familiar with it, right? Okay, the grid4 start is the default command. It's a default configuration. So if even you do not configure it, it's already enabled on the routers. Okay, and we separate them into different areas. Okay, area 0, area 2, area 2. Okay, they are in area 2, and this is the rig. Since on R6, R7, and R8, we run rig. So you can see router rig version 2, network, no auto summary, and grid4 start. It's a configuration of rig. R7 is the same. R8, since on R8 we only run rig, so you can only see the configuration of rig. And what is special is here, the configuration of spatial areas. Okay, router OSPF 100 and totally stop, totally SSA. Next, the other requirement is that we should use BFD together with OSPF and change some of the ports to be point-to-point. The computer with the broadcast, or by default, the network type is broadcast. And in the broadcast network, if we use OSPF, we should elect the DR and BDR, right? But if we change it to point-to-point, there's no need to elect the DR, BDR, and we can accelerate, okay? Or we can make it faster to reconverge or to recover from the faults, okay? And about the BFD configuration is shown here, IP, OSPF, BFD. And as a requirement, the interval is about 999 milliseconds, and multiplier is 5, means 5 times. The configuration of R4 and R6 is shown here. And the Zen is about the route redistribution. The basic configuration of route redistribution is just as we can see here, it's quite easy. It's quite easy, okay? And but to prevent loops and suboptimal paths, we should use route map. You can see here on R6, we use route map 13579, match tag 13579. And then here, when we redistribute the RIP route, we will tag them. You can see we will tag them with 24680. Okay, and distribute this route map 17579 in. Actually, based on the configuration, the working principle would be, let's get back to the topology. You can see it on R6 when we import or redistribute route. The route will get the tag 13579, or you can use another tag, it doesn't matter. While when R7 learns the OSPF route, we will filter the route with tag 13579, and on R7 it's the same. We will tag all the routes with 24680, and on R6 we will filter the routes. So in this way, R6 will not learn the external route from R7, and R7 will not learn the external route from R6, and you can prevent loops and suboptimal routes. Okay, and let's go here. BGP. The configuration of BGP is quite a lot, actually, quite a lot. But these commands, these 4 commands are default. They are default, so you don't need to configure normally. And what you should configure is just remote AS, neighbor 12.0.0.2 remote AS200, and network. Only these 3, okay? Only these 3 commands are necessary. You have to configure it yourself. The other commands are default commands. And you should modify the router ID by yourself. R1, R2. is similar. But on R2, you can see next hop 0, next hop 0. This is used to solve a problem because we see that let's get back to the topology. Okay, when we see the topology, you can see the R1, for example, now here is a root. Here is a root. It will be forwarded to R2. But according to the root forwarding policy, when R1 send it to R2, and when R1 send it to R2, it's from an eBGP neighbor. And the next hop will not be modified. Okay, and R2, when R2 send it to R4, when R2 send it to R4, if we do not change the next hop address, actually the next hop address would be the interface on R1, but it's unreachable on R4. So this route will be an unused route and will be blocked from the IP routing table. So to solve this problem, the command next hop 0 is quite necessary. Okay, this is a key point which I want to see here. And for the IBGP neighbor, when you use a loopback interface, to establish the IBGP neighbor, this command is necessary to specify the update source. Just use command update source loopback 0. Okay. So the root update will be forwarded through the loopback 0. And during the configuration, when you use this command, you will see that the BGP neighbor will be down and then up again. R3 is similar. On R4, here comes the configuration of root reflect. As I said, to solve the problem caused by the split horizon, we can use root reflect or we can use the formatch. What I choose here is the formatch solution because it's quite easier. And the command just here, neighbor 2.2.2.2 root reflector client 5.5.5.5 client, and here is the same client. So in this case, we just finish the configuration of root reflector, and it will be easier for us to solve the problem of split horizon, of course, compared with the formatch. And R6, the configuration is similar, R7 is similar, R8 is similar, but here are eBGP neighbors. Okay, and next, let's see. Next is about the GRE over IPsec configuration. Let's go through the configuration together. First is interface terminal 1, IP address, source, destination. Just establish the terminal at the terminal between GW1, GW3, GW2, GW3. And next is the basic configuration of IPsec. Okay, the encryption is 3DES, authentication is pre-shared. Here, pay attention. In the requirements, we say that about this kind of parameters, you can define it by yourself. But during the configuration, what we need to confirm is that it must be the same on both sides. Okay, must be the same on both sides. And the last step is to configure OSPF. Once the GRE over IPsec is established, next is configuration of OSPF. And in OSPF, you can see we have the internal network segments. And on the other side, GW3, let's see. GW2's configuration is similar. And on GW3, we network the segments of branches. And so in this case, HQ and branch can learn the routing entries of each other, and they can establish the communication inside the enterprise network. Okay, and then for the HQ, first is about the configuration of DHCP. It's just the basic configuration. But what you should pay attention is here. How do we use DHCP to assign a static, okay, a fixed IP address to one specific DHCP client, for example, server here. Hardware address, this is a MAC of the server, and the IP address binding with this MAC is 2.200. And during the configuration, if you configure it, pay attention, the MAC address, you should modify it by yourself. Okay. And the next MSTP VRP, you can see. Okay, and spanning tree MST configuration version 2, name Ruijie, and we have instance 0, instance 10, instance 20. Instance 0 is the default instance. So here are the instances we create. Okay, spanning tree, we use this command, you can see. We use this command to modify the priority, because we said that to ensure the root election, we have to use the command to modify the span priority. Okay, and the VRP configuration is shown here. To control the VRP master, we also use the command to modify the priority to be. This is 120. This is default. Okay, default is 110. So you can see this is the master, and on GW2 it's the same. And on the access switches, you can see the configuration of MSTP is shown here. It's quite easy. Okay, and next, let's see, it's about the link aggregation, and here passive interface of OSPF to satisfy the requirement that we only use VLAN 800 to establish the OSPF network. Okay, and here servers provide telnet SSH while cannot be pinged. So here we use the ACL to match the ping packet, because ping is based on ICMP. So deny ICMP from 172.16.1.0 to 192.168.2.200. Okay, and apply it here. This is about the configuration of the IP address global binding, right? Global binding. And this is about the port security configuration. Max number is 1 as required. And then unauthorized IP address and DHCP server. This is DHCP snooping. And the IODP configuration is shown here. Okay, and interface. This is about the anti-ARP spoofing, and ARP check is enabled. Okay, anti-ARP spoofing. This is about the we call it gateway ARP anti-spoofing. And for the branch, the configuration is quite easy. The configuration of super VLAN. VLAN range, we create VLAN 10, 20, 30, and 100. For the VLAN 10, you can see for the VLAN 10 sub-interface range, we have ranges from 1.1 to 1.79. VLAN 20 from 80 to 159. VLAN 30 from 160 to 250. This is the interface range, and the enabled proxy ARP, right, super VLAN. And this is about the configuration of the super VLAN of the branch. And until now, we have finished the branch configuration of the entire topology. Okay. And I think after introducing the requirements, the related topology, related technology, and the configuration, I think you can have a deep understanding of the protocols involved in the RCNP R&S. And as I asked at the beginning, if you have finished the RCNP videos, you can review it by yourself, and based on the theoretical contents, you can do the lab. Okay, you can do the lab by yourself. Okay, and if you didn't finish the videos, please watch the videos first and then read the requirements, then finish the lab. Okay, so we hope that by this summary course, you could have a very deep understanding of the contents, and you can master the configuration of the protocols we listed here. Okay, this is about the technical part about the RCNP, technologies, RCNP lab, and next is about the you can see how to get the RCNP R&S certificate, because the RCNP R&S certificate or RCNP R&S exam is a little from RCNA R&S, RCNA WLAN. So here we want to share some points with you. Okay, so next maybe let's welcome Erika to share about the RCNP R&S certification policy with us.
Okay. Thank you, Alex, for the summary part. And at the end of today's training, I'd like to synchronize you with the news that the RCNP routing and switching certificate exam is now available on Pearson VUE platform. You can enter the website and make an appointment for the exam now. And next, I will synchronize you with some basic information for the certificate exam. Firstly, for the RCNP routing and switching, RCNP provides free online course for you to study. You can find the learning resources on both e-learning and YouTube. The second one is the examination. Next page, please.
Okay.
The second one is the examination point. The course includes 3 parts: switching, routing, and security. The detailed technologies are included in the online course. You can learn the details in the videos and prepared well to take the exam. And the last is about the exam information. The last page, please. For the RCNP R&S, the exam has only one part. It's a written exam, including the key technologies from the exam point we've just seen in the previous page. And for now, the exam is available in Asia Pacific region. Participants can find the nearby exam center and take the exam. And other regions will be open to the public soon, maybe in the first quarter in 2024. And when you select the exam on VUE platform, please pay attention to the exam ID, which is E8311. We also have many other available exams on the list, but most of them are for China mainland region. So RCNP routing and switching is a paid exam, and the price will be $320, and the exam time is 120 minutes. You need to answer 60 questions, which consists of single choice and multiple choice. If your score reaches 60% or above of the total, you are considered passing the exam. The digital certificate will be sent to your reserved email if you pass it, and the certificate validity is 3 years. That's the basic information about the RCNP routing and switching certificate exam. You may scan the following QR codes to find the details about the operation guide and the link to the web page. And all the latest training information will be updated on your official platforms. If you have any other questions, you can ask now or contact us via the email at the bottom.